So I went over it maybe a little too fast last time, but yeah, I'm going over this algorithm. So I wrote this multiplication subroutine in our own assembly language that's assembled by a Python script into an Intel hex file format, which is burned by the east-ward prom programmer. And this is the source code for subroutine. You don't really need to exactly understand how it works. It looks like a lot of code. It's just because most of our register transfers are through the T register, so we have to do a lot of stuff to do really simple stuff, if that makes any sense. Something like move the A register to the B register, for example, you actually have to use T as an intermediate buffer. And that's just because we are limited by the amount of address lines on our east-ward proms for our control unit. So we really didn't have enough opcodes. We have something like 64 opcodes, so actually implementing register-to-register transfer for all of our registers. We have a fair amount of registers. So let's go through this kind of board of what we have. We have C, T, ALU input registers A and B. We have 16-bit program counter, I and J registers, index registers for any variable holding or arrays or anything that you want to access in RAM. And we also have stack pointer too. Stack pointer doesn't drive the data bus, so you don't have to worry about register transfers for that. And we also have instruction register. That doesn't drive the data bus, but the status register actually does drive the data bus. So 1, 2, 3, 4, 5, 6, 7, 8, 9 registers doing point-to-point register transfers. That's way too costly for the amount of opcodes you directly need to implement that. So anyway, so that's why this code's pretty long for just multiplication. But the general idea is that one register, you just constantly decrement that, and you eventually check when that one's 1, and then when it's 1, you stop, and you go to this return from loop section where you output and then return. And then the other register, the A register, you say accumulate the sum. So if it's like 5 times 5, you'll do it. One register at the B register will go 5, 4, 3, 2, 1, then you leave. And then the other register will go 5, 10, 15, 20, 25. And then that's saved in the A register and then return. And what's cool about this is we actually literally are using a call stack, and we actually have basically the hardware functionality of doing function calls. I think it's really cool is that we have complete code reuse in this assembly language. And this assembly language already is becoming a little like verbose, which I like. It has some higher level functionality of labels in here. One thing that would have been nicer in the long run would be to do conditional function calls, which the Intel 8080 processor had. A lot of other modern processor architectures have too. And it's totally doable. We could have done it. We just don't have enough time to do that right now. Anyway, I'm going to go through a little slower right now. So we're running 182 hertz. Let's bring this down a little bit. Let's do something like 100. Yeah, it's 130. That's good. And then when I flick this to the right, it goes high, so this reset line is fed to all these 74163 4-bit counters. And when a reset line goes high, it's no longer in the reset state, so you actually can start seeing lights flash on. And you see the sum accumulating. Right now, 6677, it's keep adding 11, 143. It's because we're multiplying 11 times 13, so it keeps adding 11. So now we're doing 9 times 9, 81. And then now we're doing 31 times 5. And it is 31 plus 31 plus 31 plus 31 plus 31. It's 155. And I can run this actually much, much faster than what I had there. So let's crank this up. All right, let's run this really fast. All right, I'm running this now at 555 kilohertz. So I'm gonna reset. It's all zeros now. Then I'm gonna flick this, 155. All right, I actually wanna see how far I can push this, so turn it down a little bit. We're doing 2 megahertz now. So reset, it glitched right there, 159. So let's bring it down a little bit. I want to see what it becomes stable. Let's do a megahertz. So we should get the result 155. Flick this, 155. So I mean, that's a really, really rough approximation, but running at 1 megahertz, and we were able to get valid results going through this whole program, which has 3 multiplication function calls. And it did actually do 31 times 5 correctly.